This glowing structure is a completed Huffman prefix tree. We have already covered the mechanics of how it is built, but simply running the algorithm leaves two major computer science questions unanswered. First, how fast is it? We need to measure its exact time and space complexity as the data scales up. Second, why is it correct? We need to prove why this specific tree shape definitively creates the most compressed file possible. Today, we are going to deconstruct this algorithm's runtime performance and formally prove its compression capability. Remember our definition of algorithm analysis. We must measure exactly how the runtime and memory requirements grow as the number of characters increases. To truly trust this compression standard, we cannot rely on intuition. We have to mechanically derive its speed and mathematically prove its optimality. The cyan dots on this screen track the first step, counting the frequency of every character in our data. Visiting each of those n characters exactly once to create isolated leaf nodes takes linear, or big O of n, time. Next, we insert these isolated nodes into a min-heap priority queue to sort them. A heap is uniquely efficient because data only travels up or down its vertical height, not through every node. Mathematically, this height is the base 2 logarithm of n, so moving a node takes log n time. Now we reach the inner loop. We remove the two smallest nodes, combine them, and insert the new parent back into the heap. Every iteration costs 3 operations, all bounded by that log n constraint. To fuse all characters into a single root, this combination process must repeat n-1 times. Multiplying the n iterations by the log n cost of each heap operation gives the dominant computational workload. We compare these n log n heap operations against our initial big O of n node creation. In algorithm analysis, the larger value dictates the final speed. The overall time complexity is strictly O(n) log n, because the algorithm's execution speed is bottlenecked by the height of the min-heap. Now let's look at the memory footprint. How much RAM is required to store the characters, the heap, and the final tree? This diagram shows a complete Huffman tree for a small dataset of exactly 4 unique characters. These 4 initial characters form the base leaf nodes, represented by n. To connect those leaves into a single root, the algorithm generated 3 internal parent nodes. We combine them into a universal equation. N plus n-1 equals 2n-1 total nodes. No matter how massive your input file gets, the total number of nodes generated will never exceed this proportional limit. Because the maximum memory scales directly and linearly with the input characters, the space complexity is tightly bound at O of n. Huffman coding maintains high memory efficiency because the geometric rules of binary trees strictly prevent exponential memory bloat. We have the speed and space. Now, the theoretical proof. Why does assigning shorter codes to frequent characters mathematically guarantee the smallest possible file size? Think of this physically. Dense, frequent characters are like heavy boxes. Rare characters are like tiny, fragile items. If you lift a heavy box 1,000 times a day, you store it right next to the door to save total physical energy. The exact same logic applies to data. Frequent characters receive short 1- or 2-bit codes. Rare characters can safely absorb the longer 5-bit or 6-bit codes because they are processed so infrequently. This equation calculates that total energy, or total data size. It is called the weighted path length, the sum of each character's frequency multiplied by its code length. An optimal compression algorithm must minimize the final sum of this exact equation across all characters in a file. This presents a risk. Greedy algorithms typically lock into immediate, short-sighted choices that fail to achieve long-term optimality. True data compression relies on minimizing the overall sum of every weighted path across the entire character set. To prove Huffman coding achieves this, we use the exchange argument, a formal mathematical proof common in university-level algorithmic analysis. This chart represents a hypothetical tree. Assume it's optimal, but notice the two lowest frequency characters are placed high up. Rare characters have shorter codes than common characters located deeper. Let's execute a theoretical swap, physically trading the positions of the high-placed player characters with the deep-placed frequent characters. Watch what happens to the weighted path length. The file size decreases. Assigning the longest code paths to the absolute rarest characters mathematically reduces the total bit count. Because our swap actively improved the final file size, our initial hypothetical tree was not actually optimal. This swap proves an unbreakable rule. An optimal tree must always place the two lowest frequency characters as sibling nodes at the deepest possible level. Huffman coding's greedy strategy explicitly forces the two lowest frequency nodes to combine at every single step of its execution. Because every greedy step perfectly aligns with the exchange argument, the algorithm is recursively guaranteed to produce the most mathematically optimal prefix tree possible. To recall these core metrics on an exam, use the FHTSC framework: frequency, heap, tree, shortcodes, compression. Keep two common misconceptions in mind. First, Huffman uses a min heap, not a max heap. Second, it is strictly lossless, meaning zero original data is destroyed during compression. Despite its theoretical origins, this optimal algorithm forms the backbone of modern data archiving, including the zip files you use every day. It is also the hidden mathematical engine inside lossless multimedia compression, like PNG images and PDF documents. Before modern software, this exact compression logic was hardwired into early telecommunications to radically reduce physical transmission times over telephone lines. We have mapped the algorithm's mechanical speed, modeled its strict memory footprint, and formally proven its optimality. Our next intellectual challenge is taking this greedy algorithmic strategy and applying it to temporal problems, specifically job sequencing with deadlines. Huffman coding is a solved mathematical puzzle that powers the speed and storage of the modern digital landscape.